Hello everyone, welcome to another video called Quantum Field Theory. In today's video, we will be deriving cross-sections and decay rates in the context of quantum field theory. So let's begin. First off, this video is going to be in the style of my older videos because this video is going to be just a derivation, and that won't really work as well with my newer video style. So we'll be using Notability for today's video. So first of all, what is a cross-section? I don't even know what a cross-section is supposed to mean in the context of quantum field theory. There seems to be a lot of different definitions out there. Some people define a cross-section as like the classical cross-section where you have like a source, like a proton, and you're firing some particles at the proton, and they'll like deflect off the proton, and the cross-section area is the physical area that you get when you shoot particles at the central proton. And in that sense, the larger the cross-sectional area, it means that more particles are scattering off the central target. But in quantum field theory, although cross-sections have units of area, I don't think they actually correspond to physical area. So some other texts would describe cross-sections as a probabilistic sort of thing, where it tells you like the relative probability of different scattering events. I'm not really sure. But in today's video, we'll be focusing on the definition that is used in Short's QFT book, where the cross-section is defined as the number of particles that are scattered per time times the flux, where the flux is defined as the density of particles multiplied by the velocity. So the motivation for this is that in quantum field theory, almost everything is probabilistic. So say you have an electron, and you're firing that off a positron. There is a non-zero chance that these particles just fly through each other and don't even interact, right? So with cross sections, we're looking at the actual number of particles that do get scattered per time times the flux, or per the flux. So what this flux means exactly is if you have a beam of particles and you're shooting them at a central target, so here you have a target, it's looking at the number of particles in that flux and the volume that they actually encompass. And if you're looking at scattering of two particles, which is easier to work with, so you say you have, again, an electron and a positron heading towards each other, and then the velocity here, well, here we'd have two particles in the beam, right? And so the velocity here, what it means is the relative velocity between the two particles. So the goal of today's video is to relate this cross-section to the probability, or to the matrix elements. Now note that the experimental probability that the scattering happens, so the probability that the scattering happens is given by the number of particles that actually do get scattered. So the number of particles that are scattered divided by the total number of particles divided by the total number of particles. So the total number of particles, well, let's just call it n, okay? N particles. So when we talk about measuring probabilities, what we actually mean is just shooting a bunch of particles at each other, dividing the number of particles that actually do get scattered by the total number of particles that we actually had, pretty much. Now here we have the same thing in the numerator, right? So we can just write the number of particles scattered as the probability times the total number of particles, n. So that means that the cross-section is just the total number of particles times the probability that the scattering happens divided by the time times the density times the relative velocity. So that's how we can actually introduce the probability into the cross-section. So it's a pretty neat trick. And now you have to note that the density is defined as the total number of particles that we had divided by the volume that they're actually encapsulated in. Which means that the cross-section, therefore, is equal to n times the probability. Let me just call that p. So n times p over time times n over v, right? And that's just going to correspond to v over n. So v over n. And then times this. And the n's will cross cancel out. So then we have v times the probability over time times the relative velocity. So now what we have to do is look at this probability over here. Like, how is probability related to the matrix element? Because the probability isn't exactly equal to the matrix element, right? The probability is equal to the S matrix, at least the square of the S matrix. Oh wait, no, you don't talk about that yet. Sorry. So now what we can look at. So now what we can look at is the differential cross-section. And that's an infinitesimal cross-section. And that's going to be equal to the volume, again, over time, times relative velocity, times an infinitesimal probability. Now what is the infinitesimal probability supposed to be equal to? Well, if you think of it this way, the probability is going to be a function of momentum, right? In quantum mechanics, the probability is a function of, at least since we're dealing with momentum eigenstates, we should expect the probability to actually be a function of momentum. So for example, let's actually say graph some arbitrary function. Let's call it phi of k. So here's k. And the squared value of phi of k integrated over momentum gives us the probability of finding the particle as having some momentum, which is the question that we're asking in this case. We're not asking about like where the particle is. If we're asking about where the particle is, then our density will depend on position. But in this case, we're asking about like the momenta or the energies of the particle. So that's why it's going to depend on the momentum. Now, since it depends on momentum, we should expect dp to be written as the form of like something and then dk. But we can actually get a bit more specific. We can actually write dp in terms of dn. Since recall that the particles are actually in a box, they're in an actual beam that has a volume. We know from quantum mechanics that if you have a particle in a box or a well, hint hint, that the momenta of the particles are going to be quantized, where k is going to equal n pi over L, the length of the box. Or in this case, since we have 3 dimensions, we will have different values for each momenta direction. N pi over Lx, n pi over Ly. dp written out as the probability p times dk, or d3k, since we have 3 momental directions. And recall that d3k is just dkx, dky, and then dkz. And now we can rewrite that as dn pi over ly, dn, technically this should be like nx. And then we'd have pi over lz, and then dn. And that can be written out as pi cubed over lx, ly, lz, and then this over here. And this is just going to be the volume, right? So we have that the momentum differential is just pi cubed over the volume times the infinitesimal, I guess, like n mode number. And then for historical reasons, I guess, we actually write this as 2 pi cubed instead. And we can do this since we said that k was equal to n pi over L. It's also equal to 2 n pi over L or 3 n pi over L. Doesn't really matter as long as you adjust n. So for whatever reason, we just write this as 2 pi cubed over v, and then times this over here. Now we can also write out the probability in terms of the n now, right? Since the probability depends on momenta, which depends on n, we can write it as this instead. Now we can use the fact that this over here is going to equal p times v over 2 pi cubed and then dk, where k, or technically speaking, is the range of momenta for the final particles. So the particles that come out. Now we have our differential cross section, therefore, is equal to v over t times v1 minus v2, then times dp, which we rewrote as this over here, which can be written as this over here. So p v over 2 pi cubed, and then times this over here. Now we want to relate the cross section or the differential cross section to the actual matrix element, and we can do that via the probability over here. So the probability is equal to this over here. This is the S matrix. This is the thing that we used Feynman diagrams to calculate, and we define something called the normalized probability, which is the same thing but divided by these terms over here. And the reason as to why we're dividing by these terms is to actually cancel out the volume terms that still exist in the numerator. We're going to go ahead and substitute the normalized probability in for the probability, pretty much. So what is this going to actually be equal to? Well, our initial state consists of two particles that are being scattered off each other, right? So we could write it like a conjugate K1, a conjugate K2, acting on the vacuum state. But for whatever reason, people like to input this factor in front of the creation operators to define the normalized initial state. And therefore, the conjugate of the initial state upon itself is going to be 2e1, 2e2, and then some delta functions. Delta of k1 minus k1, which is just 0. And then 2 pi cubed delta of k2 minus k2, which is also 0. Similarly, what is this going to be? Or our final state can have any particles it wants to, and so can our initial state, but we want to consider two particle scattering. So our number of particles in our initial state is fixed, whereas for the final state it's not. So our final state in general can have a bunch of particles. You have like k1, I guess, prime, a conjugate k2 prime, a conjugate k3 prime, as many particles as it needs, acting on the vacuum state. And then again, for whatever reason, sometimes we just scale this by a factor of 2e1, 2e2, 2e3, and so on. So we can just write the final state out, and then we have a series of a conjugate k, k1 prime, a conjugate k2 prime, all the way to a conjugate kf prime acting on the vacuum state. And therefore, this inner product is going to be equal to this over here, 2e kf, 2 pi cubed, and then delta of 0. So that's our inner product between our final state. And basically, what we can do now is we can notice that our delta function. This is a trick that we use like all the time in quantum field theory. I think we've already used it in this series so far. Where our delta function is just equal to 1 over 2 pi times the integral of e to the I kx dx. This should actually be, well, this is true, but we're looking at k instead. So this should be this is right. This should be delta k And since we have three momentum is pretty much the delta function for K1 times the delta function for K2 times the delta function for K3, pretty much. So delta of K for three momentum is going to be 1 over 2 pi cubed delta of e to the I kx over the volume. And since our particles are actually in an enclosed volume, this means our position variable isn't going to run from minus infinity to infinity. Instead, it's going to run from, like, I don't know, whatever this Greek letter is to this Greek letter. And that's going to cause this to just give us one big volume V. So we have delta K equals V over 2 pi cubed, and therefore delta of 0 is equal to that. So basically, this means that we can rewrite this as 2e1, 2e2, and then we had 2 pi cubed times delta of 0, but that's just v over 2 pi cubed. So we can just write that as v squared, since we had two delta zeros, right? And then for the final state, we would just have, yeah, actually this should be, I think, f. This should be f equals 1. And then delta of 0, which is just going to be v. So this means that our probability, our normalized probability, which was, recall that it was this over here, over this means that it just turns into the same thing over 2e1, 2e2, 2, and the weird product, f equals 1, 2e_kf, and then v cubed. Now what we can do is plug this back into the differential cross-section, plug this back into here. That's going to end up giving us, and now, I guess naively, we could just integrate over both sides to get the total cross-section, but that would actually be premature because it turns out that this S matrix contains information about volume and time. So looking at this S matrix, we can rewrite this as this over here. We have I 2 pi to the 4th m. This is the non-trivial part of the S matrix, where we call this the matrix element. And it's kind of confusing terminology. And if you were to square this, what you would get is where m squared is defined as this squared. So essentially, also the I goes away due to complex conjugation. So basically, what can we do now? Well, we can use the same trick as before. By the way, this delta of p, this just stands for the initial momenta, the sum of the initial momentum of the particles minus the sum of the final momentum of the particles. Now, in real life, momentum is conserved, at least in these cases. So this is going to end up being 0, right? So this is going to be delta to the 4th of 0. And we can use the exact same trick as before. Delta of k, right, was 1 over 2 pi cubed, blah, 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 yada, 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 right? And due to some volume stuff, this just turned out to being v over 2 pi cubed, right? But here we actually have 4 momentum, right? So this is going to be delta of k mu, pretty much. That's 1 over 2 pi to the 4th, then, integral of e to the I. Now, technically speaking, right, this is a sum, right? It's a sum over the 4 momentum. So it would be like p sum of pi minus PF. But we can just pretend this is just like one thing over here. Basic idea stays the same. Then over 4 volume. Now 4 volume is just going to be the dt and then 3 volume, right? And again, using the same logic, the particle is in a box, right? So the spatial integral is going to be finite. But what about time? Time is still going to go from minus infinity to infinity, right? Well, this is where the argument gets pretty weird. If you think of it as the particles are in a beam, and the particles are existing in a finite range of time, basically. So the particles just come to existence at one time and then just like go bye-bye at another time, then time can be finite as well in our integration limits, which means that this whole thing is going to just turn into a VT. So this is going to give us that delta of 0 is VT over 2 pi to the 4th. I know the argument's kind of weird. I can elaborate in the comments if you guys have any questions on that part, by the way. But basically, that turns this into a VT over 2 pi to the 4th, which turns this into just a 2 pi to the 4th. But what about this extra delta sitting right next to it? Well, we're not actually going to touch that one for now. I know it sounds kind of like arbitrary, but it'll make sense later. So we have 2 pi to the 4th VT delta of this and then m squared. Okay, and that's just for the numerator. So now we have our differential cross section is v squared over t v1 minus v2. This numerator, which we said is 2 pi to the 4th vt. So now we get this over here for our differential cross section. Notice how these terms over here cancel out with the v cubed over here. And the t over here cancels out with this t over here. So as a result, our differential cross section is going to equal this right over here, since those terms canceled out. And now what we can do, since this term is like really, really ugly, we can define some variable d pi, and we call this over here the Lorentz invariant phase space. And it is actually Lorentz invariant. And therefore, with this definition, we can define the differential cross, we can find that the differential cross section is equal to the matrix element squared over v1 minus v2, 2e1, 2e2, and then just multiplied by the differential of the Lorentz invariant phase space. And basically, what we could do is just integrate this to find the total cross section. It's just the integral of this right over here. And in the next couple of videos, we are going to calculate this cross section for various processes. So yeah, now what does this actually mean? So over here we had this phase space thing, right? And note that these are final momentum, right? We're integrating over the final momentum, not the initial momentum. And we still have this delta function over here, and it's telling us that the momentum is conserved. Yes, it's going to technically be infinite since it's delta to the 4th of 0, but we just kind of ignore that, I guess. It's enforcing momentum conservation. And basically, with that, we're pretty much done here. This is our actual, they call it the Fermi's golden rule. I think that's what the kids today call it. Now, I know that the steps we've used might seem confusing and a bit unmotivated, but let's backtrack to the main idea of what we're doing. So we defined this quantity called the cross-section, which is supposed to be something that you can actually measure. And it's just the number of particles that scatter times it's the number of particles scattered per time per the flux. That's what it is. through a series of arguments, we've derived the formula for the differential of this cross-section being this over here. Let me just write it in a clearer fashion. It's this right over here. You have a 2 pi. And basically, we can just integrate this to get the total cross-section. That's pretty much what we're doing. Now, there's a very closely related concept in quantum field theory called the decay rate, where the decay rate is defined as the probability, not probability, it's defined as the number of particles that decay per time. And through literally the exact same argument, right, you would find out that the decay rate, or the differential decay rate, is equal to m squared over 2e1, and then this over here. Through literally the same argument. I hope you guys can see why that's the case, because we can write this over here as the probability, right, that the particle does decay times the total number of particles. And that is very similar to this formula over here for the cross section, the total number of particles that scatter times the probability. The only difference is that we don't have the density and this weird thing over here. So it makes sense that our final answer should just be the same thing, but not include this, and should only have one of this, since we only have one particle coming in. So yeah, that's pretty much it. And that might be a bit confusing as to why we have the concept of a decay rate in quantum field theory, because our particles, these are asymptotic states, right? So if there's a chance a particle decays in the far past, well, that means asymptotically in the future, the particle will be decayed, right? There won't be a chance it does decay. It will decay in the far future, right? So the argument around this is to say that, oh, we can just have our interaction be adiabatic, meaning that the interaction slowly turns on in the middle somewhere. And with that, like, it makes sense. But in my opinion, that's a dumb argument, because, like, hey, in real life, interactions aren't adiabatic. Like, you have a proton and an electron, they are interacting, right? Or what I mean is that the coupling that controls the strength of this interaction, which is alpha, that's non-zero. It's not like nature just like turns it on and off, like, to help make the math easier. It's always on, right? So we can't really use that argument, but people use it anyways. But yeah, but just ignoring the subtleties there, we still use decay rates in quantum field theory. And this is how you would calculate the decay rate. And by the way, a decay in quantum field theory, it just means that you have one particle, and the particle doesn't split. You have to be careful with the terminology. Decays in quantum field theory aren't the same things as like nuclear decays. With nuclear decays, the particle literally just splits into smaller pieces of itself, right? But in quantum field theory, the decays, it's more so that the particle just turns into a bunch of particles, right? Rather than splits into a bunch of particles. It's kind of weird, but that's what we call decays. And that's pretty much it for today's video. I hope this video made sense. I know it might be a bit confusing. In our next video, we'll calculate the cross section for like some like sort of scattering process. I don't know yet. I'll decide it in the next video. So yeah, thanks for watching. Bye.